This topic here will be the last one, and probably we will cover it today or and tomorrow. So let us go for sharpening and edge enhancement. We already know a little bit how we will do it. So we will introduce a high pass filter, and then this high pass filter will be added to the original image. Okay, so let's start with this. Okay, so I think there is a better way to present this idea. So what we want to show, is something that you already know for 1D sequence, but we will do it for 2D sequence. Okay, so what is the property that you know from 1D sequence? So what is the Fourier transform of the derivative of a sequence? So let's say that you know a sequence, you know that its Fourier transform, and you know its Fourier transform. Let's write it like this: x of f. And for us, Fourier transforms are always red, so let's make them red. And what is the Fourier transform of the derivative? Let me write omega. Probably you are more used to omega. So you know it is this one. Okay, we will not prove it for 1 dimension. We will prove it for 2 dimensions. Okay, so we will have now. We have 2 derivatives. So we have 1 derivative in x, 1 derivative in y. Okay, so let us write the equivalent. So we have an image. We have the Fourier transform of that image. Right? So we have the Fourier transform of that image. We have to associate with frequencies, omega x and omega y. And we want to compute the derivative. Now, derivatives are partial derivatives because we could compute the derivative in x or y, so that is by this partial derivative. So we have the partial derivative, and what we want to show is that this is omega x Fourier transform. This is what we want to show. Okay, so let's see how to show that. Okay, so this should be good. Okay, so let us start with the inverse Fourier transform. So let's say that you are given the Fourier transform and you want to recover the original image. Then we are dropping all these kind of constants, and we are concentrating on the important part of the Fourier transform. So these are continuous images. So this will be an integral, and then we have the Fourier transform, and then we have the inner product between the frequency vector and the space vector. And I will write it explicitly. Normally, I use this angular inner product notation, but today I will write it explicitly. And then we have differential of omega x, differential of omega y. Okay, then this is the inverse Fourier transform, right? Okay, so this is the inverse Fourier transform. Okay, so now let us calculate the derivative of this. Okay, so I want to compute the derivative with respect to x of this thing. Okay, that will be, let me write the derivative in blue. Okay, so this will be the derivative of this thing here. Okay, then we have the derivative of an integral. So an integral is like a sum. Okay, so the derivative of an integral is the integral of the derivative. There are some constraints to do that, but normally you can assume. So the integrand needs to fulfill some properties so that they can be interchanged. But let us assume that normally well-behaved functions they fulfill these conditions so that they can be interchanged. Okay, so we can put the derivative inside, and then we have something that does not depend on x. So this is a constant with respect to x. So we go inside. Okay, so let's do it in small steps. Okay, so now this will be the integral. This is a constant, say. And then we have the derivative. Of and now we have to differentiate this with respect to x. This part doesn't depend on x, so we can write that as a omega x. Okay, so this is a constant again with respect to x, and the only part that depends on x is this one. So this is the integral of minus infinity to infinity of this part. Now we differentiate that one. So with respect to x, that derivative is j omega x each x. And then the remaining and then we regroup the terms. Now I will rewrite them this way: minus infinity to infinity of I need so that it looks more like j omega x I. And now we put these two together, and I already use that. There should be a minus. I have forgotten. No, that's fine. That's fine. Okay. So I have recovered again the vector notation because now it is more convenient. Okay, so now let us look at the two results. Okay, so we have, this is an image. So the derivative of I with respect to x is an image. Okay. So this is an image. And this image is the inverse, let's write the inverse Fourier transform way. So those are the coefficients of this image. Because if I take those coefficients, the Fourier coefficients, and do the inverse Fourier transform, I recover that image. Do you see that? Yeah. Okay, so like this, we have shown that this is actually the relationship between the Fourier coefficients of the derivative, the Fourier coefficients of the original image. So you have to take the original image, multiply by this. Okay, so how does it look like? This is a Fourier transform. This is a filter, right? This, do you remember the relationship between, you have an input image, let's say, you go through through a kernel, and then you get another one. So if you do it in Fourier space, the Fourier transform of J is H, the Fourier transform of H times the Fourier transform of Y. This is the structure that we have here. This is our kernel. So we have applied the linear linear transformation to our input image. That is this one. So how does the filter look like? So let us try to represent here in the, this is omega x. Let me try omega y, omega x. And I will draw only because the filter is complex, okay? So I will only draw the module of H as a function of omega. Okay, so it is the module of this thing is the module of omega x. So it is a filter such that at low frequency of omega x, this is omega x. So at low frequency of omega x, it is low. It looks like an absolute value. So it is something like this. Okay, but it is a plane. Okay, so I'm very bad at drawing, but you can imagine this is a whole plane, and this is another plane. So if you look from the omega y, so these are two planes. If you look from omega y, so omega y is now pointing out the screen. This is omega x. This is the module of H. Looks like this. This filter. So those are two planes. If you look from here, this is what you see. Very bad at drawing, so. But those are two planes. Okay, so let us put a name here. This is omega y. Omega y is coming out from the screen. Okay, so we know now how to compute derivatives with respect to x. What about the derivative with respect to y? So now we will not show it, but you can imagine what is the result. So the result is if you want to differentiate with respect to y, now the filter will be the same, but now the frequency by which you have to multiply is omega y. And these are high-pass filters. These are high-pass filters because you're eliminating here. You're eliminating the low frequency components and you're boosting the high frequency components. Okay, so this is kind of the same result, only that he's using V and U that I find them confusing because you never know which one goes with which, omega x or so those are the two frequencies in x and y, and then he's keeping all these constants that we don't care so much about those constants. Okay. So the important part of the filter is that it grows with the frequency, whether you have to multiply by 2 pi or not. Those are small details. Okay, so now. Yeah, this is the same result that we had on the whiteboard. So the Fourier transform of the derivative with respect to columns is x, is proportional, that is what we have, to the frequency in x times the Fourier transform of I, and the same when you compute the derivative with respect to the rows. Okay, then. Okay, so now can I compute more derivatives? Okay, so now I can, we associate derivatives to edges. Okay, so these are edges in this direction, these are edges in this direction. Can I have a detector of edges in both directions? You can. All you have to do is to compute. So for instance, let's say that I want to compute the edges in the diagonal. So edges in the diagonal would be so I can add both, not edges in the diagonal. I can add the edges vertical and edges horizontal. So I can add these two, and then the Fourier transform of this, Fourier transform will be j omega x plus j omega y, and then the Fourier transform y. You see, so I can add both because they are linear systems. So what is the equivalent of this? What is the drawing for this linear system? So you have an input image, then it goes through a couple of systems. One is frequency response is j omega x, the other one is j omega y, and then you're adding both. And this is your output. Okay, so now let us say that I want to compute the second derivative. Okay, so I have an image. I want to compute the second derivative. So I want to compute the derivative with respect to x. And now another derivative with respect to x again. And then I will have here the second derivative with respect to x squared. Okay, so it is very simple because what is the Fourier transform of that image? So this is j. Let's make it black. This is j. This is j. Okay, so what is the Fourier transform of j? So the Fourier transform of j is I have to multiply by this one. I have to multiply by this one. And those two are linear systems, so I simply have to multiply the transfer functions. So this will be j omega x squared, and then the Fourier transform y. Like this j. So now, if you want to compute any derivative with second derivative, third derivative, any derivative of an input image, you simply have to take this derivative operator and power it to the power 2, power 3, power whatever. And this gives rise to a very interesting concept that is, okay, so now we know how to compute any derivative alpha. So alpha, this is the Fourier transform of this. So let's say the Fourier transform of this. It is j alpha, so j omega to the alpha and j x omega. To the alpha, let's write the vector. Okay, and alpha here takes the values 1, 2, 3, so on. Why not taking, there is nothing that prevents us from taking alpha equal 1.75. So we can immediately compute something that are called fractional derivatives. Fractional derivatives. this is a very nice concept. So it is a generalization of the derivative. So you know, already you know by calculus how to compute the first derivative, the second derivative, the third derivative. But now you can calculate in the Fourier space, you can calculate 1.75 derivatives or whatever number derivatives. So simply you have to do the Fourier transform of your signal, multiply by this filter, and then do the inverse Fourier transform. So this is very nice. Okay, what else do we have here? Yeah, so nothing special. So we can add first derivatives, we can add second derivatives. So I can compute the second derivative with respect to x, second derivative with respect to y, second derivative with respect to x, and we already know how to handle that. Okay. Yeah. So let us this second derivative. There is something that is, I think, interesting. That is in the slide. That is okay. So j squared. So j squared is -1, and then we have minus omega x. So this minus that is in the slide, this minus here comes from the j squared. And in particular, this operator here, it is called the Laplacian. So if you add, so you have an image, and you go through the second derivative with respect to x, and the second derivative with respect to y, and you add both, this is called the Laplacian of I. And it appears, it is an operator that appears very often in images. Okay, so here we have it. Okay, good. Then, so now we have two ways of sharpening. So we have, okay, so let's say that I want to sharpen anything. We did it before in MATLAB, but let us look at the theory of this. Okay, I want to sharpen anything. So what I have to do is this image will be adding something that computes the edges on this edge. And this edge can be, so this is an edge that detects edges. And we have two ways of computing those edges. We already know the two. So one is in real space, and the other one is in Fourier space. So in real space, what we have to do is to convolve with a kernel that computes derivatives, and we already know a few of those kernels, so we can know this one, we know this one, all kind of combinations, and also these ones are also one. So there are a few kernels that compute derivatives and in different directions, and we can add them and so on. The other one is in Fourier space. So in the Fourier space, you multiply by, if you want to compute the derivative with respect to s, by this one, if you want the derivative with respect to y by this one, and you can construct again all kind of combinations. What are the properties of this kind of kernels? So we already saw they have kind of this shape. So in the frequency axis, they have this shape. Okay, and this shape is the absolute value, or similar to the absolute value of x. And label will reach your axis. Okay, now, why don't we generalize this? So this looks like, they look like planes. Why don't I take something that looks like, kind of has a similar shape, so it is kind of cone, but now in all directions it looks the same, because now the different directions are treated differently. This direction here, omega x, behaves like this, but in all the other directions it behaves, the filter behaves differently. So if I want the filter to behave the same in all directions, it needs to be kind of circularly symmetric. You agree with that? So let us design this filter. So let us design a filter that is a kind of cone. Okay, so it is circularly symmetric. This line here is omega x, absolute value of omega x. So, what is this? How to design this filter? It's very easy. Why don't I make the filter to be equal to the module of omega? So if omega, so in particular, if omega y is equal to 0, this filter is equal to the absolute value of omega x. That is what I want. And in particular, if omega x is equal to 0, this is the absolute value of omega y. And again, that is what we want. Okay, so then all we have to do is to compute the module of omega. So this will be omega x plus omega y. And that is what you have there. And then you put some constant in front, because as we did before in math, so you will add the original limit plus alpha times the derivative. So that alpha goes here. That alpha goes here. So you're modulating your edges, multiplying by alpha, and then adding alpha times your edges to the original limit. And these two alphas are different. Okay? This alpha. So this is the derivative, the one of the derivative. This is the one that scales the edges. Any questions? No? Okay, then let us see some examples. So let's say that we have this image. That is the power spectrum of that image. And we already recognize, okay, these lines are related to these small gaps in different directions. Okay. And now let us use the upper branch. Okay, so the upper branch we are convolving with this kind of filters. We're convolving with that kind of filters. We compute the power spectrum. So this one, for instance, is missing the zero in between, but we don't care. They all belong to the same kind of the same family of filters. So we compute the power spectrum of this. So you do the Fourier transform of this kernel, and you represent that Fourier transform, and this is the power spectrum. Now you multiply the input, multiply the power spectrum of your image times the power spectrum of your filter, and you have the power spectrum of the output. And then this is how they look like. So we only see the edges in this direction. And we are blind to edges in this direction. So here there is an edge, but it doesn't give any response. We are blind to this kind of edges. And then the same, and we are, okay, so let's look at this. Okay, so our filter was, let's do it here. So our filter in that case was h of x of x and y plus delta xy minus delta x minus 1. So those are the edges in that direction. Okay, so what do we have there? Okay, so if this is our filter, then at this point, let's reproduce the diagram for not plugging it. So we have go through the filter, and then we are adding with the factor of alpha. Okay, so at this point, we have, let's make it green. So we have I convolved with delta, but this is I minus y minus I x minus 1 I. And then we are adding both. Okay, so we have I both sides plus alpha I x minus alpha plus I x minus 1 I. And then you can regroup these as 1 plus alpha I minus alpha I x minus 1 I. So this is the kind of expressions that we have there. Okay. So if you make alpha equal 1, you have this one.
Can you put the no me can get
Okay, so we're here computing these differences that we already understand where these kind of expressions are coming from. And then we can follow the other path. So on one side, we are computing the sharpening in real space. On the other side, we will do the sharpening in Fourier space. So, and you already recognize this kind of expression. So this is the modulo of omega times the Fourier field, the Fourier transform. So this is the original image, the original power spectrum, and then this is the one that is modulo of omega times the Fourier transform, and then the inverse Fourier transform. And we see that it is an edge detector, but now in all directions at the same time. And then you can add both. Okay, so this is just to highlight where the borders are. So now you can threshold the high-pass filter image. So that is the original image, and the high-pass filter image, this one. So this one here, and then you put a threshold to see where the borders are, and those are the borders. And then instead of the modulo of omega, you can compute the modulo of omega squared. This is this one. And now you understand what you are doing. So what you are doing is you are multiplying two of these kind of filters. So we have it somewhere, if I can find it. Here. So this is the modulo of omega. Well, in this example it was j omega x, but this is the first derivative, and now you put the second derivative. So what you are doing is boosting this kind of responses. So the Laplacian, so let's say that you have an image, you go through the first filter that has this response. This is omega x, omega y, and then you have this one. This is h. And now you apply the same, so the same h. But now the multiplication of the two. So this is omega, this is omega. And now the multiplication of the two is the same as if your image goes through a single system whose impulse response is omega squared. And modulo of omega is a line. Modulo of omega squared is a parabola. Omega y, omega x, modulo of h, but now you have a parabola. So this one goes as omega squared, not as omega. This one was omega, okay, but this one goes as omega squared. So you are boosting even more the high frequencies. So the more derivatives you take, the more you boost the high frequencies. And this is what we see here. So only very strong edges have a high value in this image. And you can add it to the original one, and to this one we will call it quadratically enhanced, and the quadratic comes from here. So this is a quadratic term, this is omega squared, while this one here goes with omega, goes with the modulo of omega. And then the strongest edges are the ones that have high value. So we can compare this one with this one. So here we have many more edges, but here only the strongest one survives. Okay, then I think this one, I think it is better explained here. So this is what we want to have. So let's have that result. So there are two results there. So I think they are better explained in this way. Okay, so let's have it here. Okay, so the first result is something that is called directional derivative. Directional derivative. And what is that? Okay, so let's say that you have a function. This is y and I of xy. And this is our image, okay? So it has some shape there. So this is our image. We know how to compute derivatives in this direction that are partial of x. We know how to compute derivatives in this direction. Let us look from the top. So if we look at from the top in this graph, would look like this. So this would be y, this is x, this is y, and then we have some shape on it. So let's make this is our image. So let's say that our image looks like this. This is our image. And what we know is how to compute derivatives in this direction. So you are in any point, you know how to compute derivatives in that direction and in this direction. But actually, by calculus, you know that you can compute, if you have a function like this, you can compute derivatives in any other direction. So let's compute the derivative in this other direction. And there is a property. There is a property that is the derivative in that direction. So now it is the direction derivative with respect to the direction u. Okay. So we can compute the derivative of I with respect to the direction u. U, that is this vector here, u will have two components, the ux and uy. So those will be the components of u. Turns out, we will not show this, okay? But it turns out that this is ux, the derivative of the image in the direction x, plus uy, the derivative of I in the direction y. So we have u that is defined like that. Let us define, you may remember the definition of the gradient of a function. So the gradient of a function was defined in this way, was a vector whose first component was the derivative with respect to x, and then the second was the derivative with respect to y. So actually this derivative, the directional derivative, is the inner product between u and the gradient. So once you know how to compute derivatives in x and y, immediately you know how to compute derivatives in all directions. And derivatives are edge detectors, okay? Okay, good. This is one result. This is the first slide that I gave. What is the second result? Okay, so the second result is the following. And I think that this way of reasoning, I think it is easier to understand. Okay, so let's say, I will do it in one dimension because it is simpler to show, but you can easily, by putting x and y's, you can easily generalize to any number of dimensions. Okay, so let's say that I want to compute the derivative with respect to t. I will use the one-dimensional argument again of x of t convolved with h of t. Okay, so what does it mean? Okay, so it means that I have x. It goes to a convolution with h. Then it goes through the derivative. But the derivative is a linear operator. Okay. And then we have y. This is our y. Y t is equal to that. So I have the derivative of a convolution. Okay. Then Then I can, these two operators are linear, so I can swap them. So this is equivalent to this other system. So first you compute the derivative, and then you go through the filter. And because the two operators are linear, you can switch them. Okay, so but then that means that that is equal to what? Okay, so that let us write y in blue. Okay, so then you compute the derivative. And then that output you convert with x. And you know that the convolution is commutative. So I could have written this in this other way too. So I could have written this in this other way. H of t convolved with x of t. And then this would be equal to x of t convolved with the derivative of h. So those three expressions are equivalent. The three give me different instructions about how to compute something, the derivative of a convolution. So you can compute first the derivative of your input signal and then convolve, or you can compute the derivative of your kernel and then convolve. And this is what we have here. So those are the three expressions that we have here. So you see, derivative with respect to some direction of a convolution, and it is the image convolved with the derivative of that kernel. And here we have the directional derivative. Then, let us look at this again. Okay, so we know already these kind of expressions where we have derivatives in this in the x direction, and we know that I can have the left derivative of the left difference, so that is 1 pixel minus the one of the left, the right difference, that is 1 pixel minus the one on the right. And those two are approximations to the derivative. But these two behave differently. So with these two, when we have an edge that goes from 0 to 1, the left difference has a high value when it goes from 0 to 1, and a low value when it goes from 1 to 0. And the right difference is the opposite. So it has a low value when it goes from 0 to 1, and a high value when it goes from 1 to 0. And then we can add the two. We can add the two, and then we can have something that behaves more or less more symmetric. And the same in y, and then we can add. So we have kind of the symmetric derivative in x, the symmetric derivative in y. We can add both, and we can use them for sharpening our images. So let's say we have this image, we convolve. Let us start with this one, so with the left difference. And here it is interesting. Yeah, it is interesting. Let's look at all these borders. So with the left difference, we start with low. So you see this a black line, and then followed by a white line. And then the addition of the two. We can have the opposite. So this is the right difference. Now we have first white and then black. And we can add both. and we can add both at the same time, and then they behave in the same way. So we have white on both sides. So we have white, then black, then white. And so, depending on what is the kernel that you use to detect your edges, you are adding this sharpening. They have different properties, slightly different, not so different, okay? But they have different properties, like white and then black, or black and then white, or having more symmetry, and so on. You are adding your edges to the original image. So now we have something that we see better the edges. We already know that we could have multiplied this and modulated it with a factor alpha, so that we don't have to add the full edge, but we can add 0.1 the edge, or 0.2 the edge, or whatever. The same in vertical, so this is the same idea, but now in vertical. And we can add both. So let's say that I want to enhance the edges, both vertical and horizontal. So this would be my addition of the 4 kernels. And now I have all kind of edges, vertical and horizontal. And because of this directional derivative, I would know even how to compute the edges in all other directions. Okay, and so now I have an image that has been sharpened by edge, vertical and horizontal edges. Okay, now let us see if we can use a low-pass filter to sharpen images. And let's follow the following path. So this operation is called unsharp masking. Okay, so we know that at the end, a sharpening is a high-pass filter, image on top of the original. Okay, so let us construct a high-pass filter image. So let us do it like this. Let me do it in the on the white. Let's go white. So we will start with an image icon. Now I will go through the Gaussian filter, low pass filter, with some sigma parameter sigma. And this we will call it, let me be consistent with it, J. Okay? J. Okay, so what is the impulse response of this in frequency? This is frequency, this is sample length. This is J. Okay, now I will construct K. Okay, let me construct K. That is this one. So this goes with plus, this goes with minus. And I will have K. Let's make it K is equal to I minus K. But J was I convolved with T, sigma. Okay, so this is the same as I convolved with delta minus G sigma. So what is this impulse response now? So this is impulse response is the opposite. It is the high pass filter. This is the Gaussian high pass filter. So let us only change. Okay, that is 1 minus Fourier transform. That's Fourier transform. So now we have a high pass filter. At this point, K is a high pass filter. Okay, what next? What do we do next with K? So now we take and construct the unsharpened image that is alpha k plus I. So it is the same that we will have. Let us now go on this side and we will subtract the addition of these two. This one goes with the weight alpha. So now our unsharpened image is I plus alpha k. But k was all these things, so let us write it now. Okay, so it is I plus alpha k, but k was this thing, plus alpha I all with delta minus g0. And then we have I 1 plus alpha, that is those two terms, minus alpha minus with this. So what I have is, this is a scale factor. This is a scale. This is a scale. See, we are scaling by a factor of 1 plus alpha. And this is a low pass filter. So I am having a sharpened image by using a low pass filter, but using a low pass filter with a negative sign. And we already know where those ideas are coming from. These ideas, so this minus sign here, this minus sign here is related to this minus sign there. Okay, so to get a high pass filter, I have to take a low pass filter and 1 minus that. And this 1 minus that translates into that minus. Whereas, and this alpha here typically takes some value between 0 and 2. So let us look at the result. So this is the original image, and then this is the power spectrum. This is the blurring, so we will use a low pass filter with sigma equal 4, and we have seen also these things in MATLAB, so we know how we come to that. And now this is original minus the Gaussian blur, so this is the high pass filter version. These kind of things, we have been talking about derivatives. Let us make a zoom of this part. So we have been talking before about derivatives. We said anything that is kind of like this is a derivative, it is an excitator. Actually, any low pass filter, so this is omega, this is h. So anything that looks like that, and this one also is an approximation of that. So we would have at low frequencies. So this one I don't know. So at low frequencies, they look similar. The main differences are at high frequencies. So at high frequencies, these derivatives here, they grow very much, while these ones, they stay. So somehow, if there is noise, these derivatives are very bad. These derivatives are very bad because we are boosting the noise a lot. And if there is noise, these derivatives are not so bad. They are saturated. And another thing, we said if this is radially symmetric, this is a cone, then we are computing derivatives in all directions. And the Gaussian is radially symmetric, so we are detecting edges in all directions. Okay, so these edges are detected in all directions. It is not X or Y. In all directions, we have in edges at the same time. And then this is the addition of the two. Okay, so it is the high pass filter plus the original. Okay, and this is the result. So we like better this edge enhanced images because our visual system like edges. Okay, and here we have the two. So we see much brighter this one. And it is because the edges are stronger. And then here we have a comparison of the four. So we have the original image, the linearly enhanced image. So this is omega squared, this is the Gaussian. Okay, so what happens with noise? So we can have two different kind of noise sources. So why do we have noise? Because if you are using a sensor, you are using a CCD camera, for instance, then there are electronic effects there, these quantum effects, that makes that randomly you detect something when there is nothing, or the opposite. There is a photon coming in, but you don't detect it. And if you have a photograph film, then these films are based on these silver alike grains. So there is the film is made of small grains of silver alike that when they are excited, they change their chemical property. And the size of these grains are random. Or we have noise in the spiking of our neurons or whatever. So let's say that so we have noise sources, and let us look at, and this noise can be independent from nearby noises. So if you are given a noise point here, you don't know what is the noise just nearby. Let us make it in one dimension. So let us depict a couple of signals. Both will be random, but they have different kind of randomness. So this is time, and let's say that this one is something like this. It is completely random. The other one is also random, but it is much smoother. So it is something like this. It is random too. But if you know one value here, okay, you know that the nearby values, they cannot be 5. So these two values, they must be close to this one. And in this signal, you don't know. If you know this value, you don't know what this one will be or what this one will be. Okay? So these kind of signals, they are called spatially independent, while these ones are spatially dependent, spatially of time. Independent of time. Okay, so what is the property? So how can we formalize this? We can do it through the autocorrelation function. So the autocorrelation function of the signal t, that is the expected value. Sorry, this is tau. This is tau. This is called the lag. Okay, so this is the expected value of x of t times x of t plus tau. Okay, in the first case, what does it mean? It means that if you take a point, This is your point T. This is your point T. This is your point T plus tau. So if you take this point, what is the expected value of this one? Do you know anything of it? That is what this expectation means. Do you know anything of it? So for especially independent signals, this looks like this. So this is sigma squared. There are small details that I'm speaking, like subtracting the mean and so on, but let us forget about it. So this is a delta. So that means if tau is equal to 0, then this expected value is something now, that is the variance of your signal. If tau is different from 0, this is 0. That means that you don't know anything. The expected value is 0. You don't know where to go. And for these ones, spatially dependent, the phi, let us plot this one. So it is a delta. Okay, so this is phi of x, tau. This is the tau axis. And for these ones, they're different from 0. Typically, something like that will represent it like this, but it can be any function. But it means that it is not 0. Okay, so for nearby tau, I know a little bit how they look like. So if you give me a sample, okay, they're random, but if you don't go too far, I can tell you a bit about what the signal will be at that tau. Okay? If you go too far, if you go to here, I cannot tell you. It behaves like random noise. I cannot tell you. If you go too far in this signal, I cannot tell you what that value will be. But if you stay close to my sample, I can tell you a bit what is the value. Okay, so that is this distinction that he's making here. Spatially independent noise. The noise, in one sense, has no effect on that of its neighbors. So the autocorrelation is an impasse. That is what we were describing in the whiteboard. Okay, and you know the expression white noise. Okay, so let us look at some other property. What is the distribution? Okay, so let's say that I look at this kind of signals once and again, many times. Okay, so I look at this kind of signals many times, but now, so they all look more or less the same. But at any particular point, they are different. So if I look at this point here, for instance, at this point here it was low, but here it is high. Okay? And if you repeat the process, they look more or less have the same appearance, but the specific values, they are different. Okay? So now you look at this point. This is time t0. This is time t0. You look at the t0. This is a random variable. If you repeat this process many times, the value at t0 will be different every time. But it has a distribution, right? It must have a distribution. What is the distribution of that? Now, I can compute. Okay, what is the distribution? What is the probability of observing a particular t0? And for instance, it can be a Gaussian. You may have heard of these signals. IID noise. Have you heard of that? No? Okay. So let us, it has two parts, this and this one. The first one is independent. The second one is identically distributed. And now we understand what it means. So the independence is referring to the autocorrelation, while the identically distributed is referring to the distribution of those pixels. So you can have independent noise that is Gaussian, independent noise that is Poisson, independent noise that is salt and pepper. And you can have Gaussian noise that is dependent or salt and pepper noise that is dependent. So those two are two different properties. And now it comes my comment. Okay, so let's say that they are independent. If they are independent, then this is sigma squared delta tau. We define the power spectrum at a given frequency as the Fourier transform of the autocorrelation. If this is a delta, what is the power spectrum? Constant, 1. So this is, if they are independent, this is sigma squared. Independent of the frequency. Let us plot that. So we have omega, we have the power spectrum of x with respect to omega, and it is sigma squared. It is flat. And now you get the name. This is white noise. White? Why do you call it white? Because the power spectrum of white light is flat. Okay, so white light is flat, and this is a flat spectrum, so you call it white noise. So white noise refers to independence. It doesn't say anything about the distribution. Okay, so now, so these comments here, they are what I have been explaining. Okay, so now, how does independent, identically distributed noise looks like in images? So they have to be independent. So given a pixel, you don't know anything about the other pixels, and each pixel will have a distribution. This is the F that I was referring to before. So the F is Gaussian. They have simulated, this is simulated data, so they have simulated with this mu and this sigma. And this is how they look like. And now we can verify all these properties, so we can compute what is the autocorrelation. The autocorrelation looks like a sigma function. We can compute what is the power spectrum. The power spectrum looks like a flat spectrum. This is the same. But let us see this with images. I think it is these ideas with images. I think it is easy. Okay, so let's say we are simulating because to understand the effects of some things, it is better to simulate them so that we can understand every part of the process. So let's say that we have a clean image, we have noise, a noisy A, and we compute the power spectrum of the two. So we have the power spectrum of the clean image, power spectrum of the noise, and we superpose both. So there is a property that you already know that, let's say, that you have this model. J is I plus N. So J is I plus N. This is the clean image, this is the noise image. What about the power spectrum? So the power spectrum of J will be the power spectrum of I plus the power spectrum of N. There is a condition for that. And this is very important condition. Normally, if the conditions are mild, we skip them. But if the conditions are not mild, we don't. I is independent of N. Let's put it. It is the same, but I think it is more clear like this. N is independent of I. And there are situations in which the noise is independent of the image. And there are other situations where the noise is clearly not independent of the image. So for instance, we have an example of microscopy. They are independent. We have computerized tomography, X-rays, computerized tomography, and they are not independent. They are dependent. Okay, so depending on the modality that you are using, you may have independent noise or dependent noise. But okay, so let's say that we have independent noise. Then, if we have independent noise, the two spectra will be added. So we add both. And then we see something. There are some frequencies at which we have much more signal than noise. And there are some other frequencies at which we have more noise than signal. So here the signal to noise ratio is larger than 1. Here the signal to noise ratio is smaller than 1. And that is why we see basically the image. So we see the balls and the cubes and so on, because at low frequencies the signal is dominating. So we see the big objects. What about the small objects, the very small objects? They are hidden by noise. So, for instance, if we look at something that is very, very, very fine, so for instance, what is the exact border of this cube? The exact border of that cube. It is a small detail, and if you zoom in, it is a little bit unclear. Okay, and yeah, these are 1D representations. Here are the 2D representations. So we have the power spectrum of the image, the power spectrum of, and here we represent the area in which we have more noise than signal. Area where we have more signal than noise, and we superpose both. And here, let's say that we have the clean image, the noisy image, that is clean plus noise. And now we boost the high frequencies. We do a sharpening as we were doing before. So the sharpening, what is it doing, the sharpening? So we already know the sharpening is multiplied by these kind of filters. So it is multiplied by this kind of filters. So that means that if we have this situation in which the high frequency is dominated by noise, then we are boosting the noise with respect to the signal at the high frequencies. And this is what we should see. Okay, so let's look at the original. This is the noisy. Now, this is the enhanced. original and enhanced with noise. Look at the background here, for instance. This part of the eye, the white part of the eye. We have much more noise in the sharpening it with noise than in the sharpening it without noise. So we are boosting the noise here. So sharpening, if you have noise, is not a good idea. And that is why this kernel that we had before, let me look for it. I don't know where it is. Somewhere here. There. It's unsharpened masking that we have with the Gaussian opacimeter. It behaves much better because at some point it saturates, while the derivatives they go to infinity. So the unsharpened mask, at some point it will not grow the noise anymore. And yeah, more comparisons. And then let's look at this effect, but now with another image. Here it is the linearly enhanced one, the quadratically enhanced, and then, so the quadratically enhanced should have more noise than the linear, and it does. Any question? No. Okay, so tomorrow we will continue with the lectures. On Wednesday we will do our own practice, and in general, to the end of the course, every Wednesday there will be practice. And when we finish with the theory, that will be only practice. Okay? So in general, every Wednesday practice, and then when we finish with the theory, all the time practice.